Hi everyone, we are students from University of Wisconsin-Madison working under the guidance of Professor Sharon Lee. And today we are about to present to you MOOD, Multi-Level Out of Distribution Detection. Let's say we have a food image classifier trained on food item images from different cuisines. And then during inference, we see this pretty bird as input. Ideally, we would want our classifier in production to say it's out of distribution, but as shown in previous literature, usually it does not do that so confidently. Here is some of the previous work which has contributed to this critical domain. Now, most of the previous methods require a full feed-forward pass, and then at the final exit, output scores such that the probability distribution of the out-of-distribution data is further away from the in-distribution. This full feed-forward pass is done for all kinds of data, simple ones like grayscale digits to much more complex scenes. In safety-critical applications like self-driving car, this directly translates into larger latency for the car to take precaution in case of out-of-distribution scenes. Which brings us to our motivating question. Can we exit early for simpler out-of-distribution data? Can we do this adaptively in some way? Presenting MOOD, multi-level out-of-distribution detection. The first challenge we addressed here was choosing the right architecture for early exits. To this end, we went ahead with multi-scale DenseNet, which comprised of blocks with multiple interconnected layers and intermediate classifiers, which provide coast-level features throughout the network. The next challenge we address is how to choose the optimal exit given a test image once we have these intermediate classifiers. We solve this with an image compressor. The images are passed through a PNG compressor, which is a non-lossy compressor. This provides us with an inherent image complexity representation, which we normalize and bucketize into k-exit buckets. This basically decides the exit we want to go with and is actually seen to work well empirically across a varying range of complexities, but more on this in the results section.
Now we can make the simple image exit earlier and the complex image exit later. So the complex image exit later and the simple image exit earlier. Now the question comes, what scoring function to use? We start to use the energy score here. However, since we have multiple exits and different images may exit at different exits, so the energy score cannot be directly applied. Hence, we propose the adjusted energy score. The left formula is for the energy score function from the paper Energy-Based Out-of-Distribution Detection, Leo 2020. The right formula is for the adjusted energy score function we proposed. In the left box plot for the energy score, we can observe the energy score for in-distribution dataset fluctuates among different exits. In the right box plot for the adjusted energy score, we can observe that the adjusted energy score for in-distribution dataset remains constant among different exits. This slide provides the average results across 10 OD datasets. The in-distribution dataset is selected as CFR10 and CFR100. From the column of the flops, we can observe that the MOOD method can reduce a lot of computational cost. And from the columns of the ARC and FPR95, we can observe that the MOOD method achieved the best out-of-distribution detection performance. This slide provides the result for each dataset. From the first figure, we can observe that the simple dataset prefer to exit earlier, and the complex dataset prefer to exit later. Hence, the computational cost increases when the complex of the dataset increases. From the second figure, we can find that for all datasets, the MOOD method The gray bar has quite competitive OD detection results compared with the optimal exit. In the summary, we propose a novel framework, multi-level out-of-distribution detection, the MOOD method. We dynamically exploit its earlier classifier outputs for OD inference using image complexity. We propose the adjusted energy score for multiple classifier OD detection, and we achieve up to around 70% computational benefit for simplest dataset, and on average around 20% computational benefit across 10 OD datasets. Thank you.